looking at this introduction to compound interest in number 3, what we see is that the difference between this and the simple interest formula is that the growth rate is being divided by n, and our exponent is being multiplied by n. That means that we are applying. It's dividing how much we're gonna like how much our interest is, right? So instead of applying 12% interest each time, it's getting cut. It's getting cut, but we're then applying the interest more frequently, right? Um, so when we start kind of plugging things into this, you'll see that n is 12 if we're dealing with months, right? So, and the rate was 12%. So I'm going to start doing part B. So our formula would look like A of t is equal to the principal, which was our initial loan of $5,000, right? Times 1 plus the rate, which was 0.12, right? Because 12%. But that gets divided by n. The number of n is the number of times the interest is applied per year. Here in this example, we're talking about monthly, right? It was compounded monthly. So we're going to divide the interest by 12. And then our exponent would be nt, so 12t. So what that does here, you can see when the 0.12 is divided by 12, instead of our interest being 1.12, right? Instead of like how in this problem over here, right? The interest would have been like the 5,000 times 1.12 to the t. Instead, over here, we actually are going to have 5,000 times 0.12 divided 12 is 0.01, so 1.1.01. So you see how the rate here is smaller, but we're going to be applying that rate more frequently because of the 12 multiplying this up here. So then we say, okay, well, how much do I owe him? How much do I owe him after 3 years, right? So that's going to be when I plug 3 in for t. So we get a of 3 equals 5,000 times 1.01 to the 12 times 3. So even though the rate that we're applying each time is less, we're applying it 12 times as much. So actually this is going to end up getting raised to the power of 36. Now you don't really have to do this in between adding up and multiplying that I'm doing, but you'll find that it kind of can make it simpler when you're plugging it into a calculator. So now let's go ahead and plug this into a calculator and we'll see what we get. And when I plug that in, I get $7,153. All right. So that's kind of a solution to number 3, looking at that. It then asks us follow up, how much do we owe him after 5 years, right? We could solve the same thing. Yeah, we could do it the exact same. Yeah, we just plug 5 in for t. Plug that into a calculator, and then why don't I have you guys tell me how much that would end up being. So go ahead and take a minute, try to figure it out. If you're watching this recording, go ahead and pause it, figure it out, and then skip forward. Yeah. Yeah. That is 1 plus 0.12 divided by 12. Right? Does that make sense? Okay. Yeah. Um, so has anyone been able to plug that in yet? $9,083. Exactly. And so then it asks us to compare these amounts to problem what we got in problem one. Now I haven't done problem one here, right? But I do know that the solution to problem one part B was 8,812, and we were given how much it was after 3 years here. So look at what happens after 3 years when we do it with monthly interest. The amount that we owe him is actually slightly more than when it was just simple interest. And when we do the monthly interest for 5 years, it's also slightly more. So what you'll find is that actually there is this because the interest that you're applying, right, on the money gets applied to itself, right? That's like how exponential growth works. We owe him $5,000, and then we add 12% to that 5,000. Then after another year, we add another 12%. But it doesn't just add the same amount each time, right? Because the 12% is applying to this guy here, right? It's like first the 12% applied to 5,000. Then the 12% applied to 5,000 with an extra 12%. Then it applies to the amount that you have there, right? So the more frequently you do that, right, by doing monthly compound interest, it actually does increase the amount of money slightly. All right.